Good morning and happy Thursday. At least that's what it is when I'm recording this. It's Thursday morning. Thursday would normally be the day we'd have this class live, so I like to record them on Thursday or at least have them ready on Thursdays. So today we're going to continue what we talked about last week. So let me go to right away Blackboard. Let me stop my video here and share this. All right, so we have Blackboard. And under courses, you will have either this one or this one. So let me go with 272, any one of them. Under lessons, this is where we were, right? We were in the second set of slides. And we'll open those up. This way you can review things, follow along if you want. Just want to make sure you know where these things are and what we're working off of. Sorry, it's moving a little slower than it normally does. So this was week 3. Of course, now we're into week 4. These slides will take several weeks to do. We've already gone through the electronic control systems overview. We talked about how computers work, inputs, outputs, the processing that happens, how they use electrical signals, ons and offs to be ones and zeros, and how those ones and zeros can be used in combination to create other data like letters and numbers besides 1 and 0. I compared it kind of to Morse code, and then I showed you the American Standard Characters for International Interchange, ASCII, the table, just so you see that these things are standardized. Your personal computer and your car's computer probably aren't all that different. Then we talked a little bit about thermistors. So next on the list, of course, is potentiometers. We saw that in my lab demo with the paper clips and a piece of paper and the pencil lead. And then switches, data streams, AC generators, DC generators, pressure sensors, other sensors. Now normally, so I'm going to go back up here to thermistors. Normally, and let me talk to you for a bit. I like to save diagnosis towards the end of the semester. The theory is that before you can diagnose something, you have to know how it works. And so I like to talk all about how things work first and then talk about diagnosis. But some things came up, and as cars come into the shop during the semester, sometimes we see interesting things, and I like to talk about them before I forget them, before you forget them. So I may have talked about this one already in the shop, but years ago, my daughter had I think a 2003 Volkswagen Jetta. And so we just talked about thermistors, which of course are temperature sensors. And so what I want to kind of talk to you about with 2 examples, this is the first one, is that the onboard diagnostics are not really perfect. They are getting better. When I first started, this was back in the 80s, there were a small number of codes. They just kind of pointed you at the system, and then you were kind of on your own. It's getting better. But I'll give you an example of where they can be misleading. Going back to 2003, this Jetta, she bought it used, but it was still within the factory warranty. So when something went wrong with it, of course, I took a quick look, but I didn't change anything. I didn't mess with anything because it was under warranty. So I just plugged the scan tool in to see what the code was and then sent it off to the dealer. So this Jetta developed a check engine light and plugged the scan tool in real quick and saw that it was a code for the engine coolant temperature sensor. So, okay, just kind of noted that, had her take it to the dealer, and the dealer put an engine coolant temperature sensor in it. Sensible, I guess. Um, so the car comes back. She drives it for a few days or a week. I don't really remember. This is back in 2005. So we're 16 years ago. The check engine light pops back on, and so I plug a scan tool back in, and it tells me again engine coolant temperature sensor. So back to the dealer. They put a second engine coolant temperature sensor in it. Is that a ridiculous thing to do? It's not ridiculous, no. You can get bad new parts. It does happen. And when you do get bad new parts, that will really screw up your diagnostics. So you can't just throw parts at something, or you will get burned by that someday. So car comes home, no check engine light, second new engine coolant temperature sensor in it. And of course, within days or a week, and I don't remember again, check engine light comes back on. Scan tool tells me same code. So back to the dealer. This time, they realize it's probably not the engine coolant temperature sensor. So what they do is replace the harness connector, the plug that plugs onto the sensor. So now instead of the factory wiring, there's a plug and four, I think there were two sensors in one. So anyhow, spliced wires. And I wasn't really thrilled with that, but if that fixes it, that's fine, So needless to say, well, no, not needless to say, but within a short time again, the check engine light comes back on, and it's again a code for the coolant temperature sensor. So this time I decide to do a little bit more of my own exploration into what it might be, because it's obviously not the coolant temperature sensor. It's obviously not the harness connector at this point. So what's left? The rest of the wires from the sensor to the computer, maybe. Maybe the computer itself, although that is less likely than probably anything else. They don't fail at a high rate. And maybe some sort of mechanical issue. So I plugged the scan tool in and brought up live data and watched the engine coolant temperature sensor as the car warmed up. And so if you've taken AC and heating, or if you're taking it now, you will have, or you will know that most engine thermostats open at, 190, 195, so somewhere just below 200 degrees. And then the engine temperature may continue to rise until into the two teens, 212, 213, before the electric cooling fan kicks on. And then the temperature kind of hangs out in that range, somewhere between 195 and 213 or 212, somewhere around 200 degrees, let's say, would be absolutely normal for it to go up a little, go down a little. So I watched the scan tool. I'm watching the engine coolant temperature sensor, and the vehicle's warming up. It's 120, 130, 140. 150, 160, 160, 160. It never ever gets above 160 degrees. So either this sensor is wrong, which, as you can probably figure, is highly unlikely at this point, right? Or the engine is actually not reaching operating temperature. So I put a thermostat in the vehicle. It was still under warranty, but I wanted to do this myself at this point. So what can keep an engine from reaching operating temperature is a thermostat that doesn't close. So I put a thermostat in the vehicle, cleared all the codes, watching the data. It goes through 160, 170, 180, 190, 195. In other words, normal operation. And that coolant temperature sensor code never came back. So what do we learn from this? We learn that the diagnostic trouble codes can point you towards something but they don't tell you exactly what's wrong. So even though the code was for the coolant temperature sensor, there was absolutely nothing wrong with that coolant temperature sensor. I'm convinced that the original one from the factory was never the problem. Can't prove it, but it was actually a basic mechanical problem that could have happened on a 1970 Chevy. You know, that here it was a 2003 Jetta, basic mechanical problem, but it manifested itself as a computer problem and a diagnostic trouble code. Fast forward to maybe 2015, 16, you know, a newer car, and I've seen them come in now with a code that actually says engine not reaching operating temperature. So the diagnostics, in other words, have gotten better, where it didn't just say coolant temperature sensor problem or out of range. It says engine not reaching operating temperature. So it's giving you a lot more to go on. And then just watching that sensor, you would see, yes, it's not reaching operating temperature. It needs a thermostat. And I've probably seen maybe 2 of those since the Jetta issue happened. So I thought that was you know, an interesting lesson in how computer problems aren't necessarily always electronic or related to the sensor or related to the computer. This was a basic mechanical issue. Second basic mechanical issue that caused the diagnostic trouble code occurred in the shop just the last couple of days, and so several of you were involved in it. If you're in the Thursday night class, you had nothing to do with it, but Monday morning we did the diagnosis. Monday afternoon we took everything apart. Tuesday morning we did the repair, and Tuesday afternoon we reassembled everything. And so for the Thursday night class, sorry, you completely missed that, but let me tell you, you didn't miss anything fun, but it was informative. We had a 2014 Chevy Equinox with a, I think, 2.4 liter. It was the 4-cylinder. It's got a 4 or a 6. Now, when I show you on all data, excuse me, the repair procedures, I'm going to use a 2015 because what I found is that the 2014 diagrams, pictures and things didn't match what we have on this vehicle. So I think it was probably a late production 2014. The registration was 2014 model year. I did not find the build date sticker on the car. I didn't look that hard. So I'm thinking it was late production, so it had the 2015 equipment on it. So let me just let's look at all data for a minute. So I have, whoops, yeah, let me get rid of this a sec. Shrink this down. Okay, so like I say, I'm going to go to 2015 because the 2014 just wasn't right. Chevy truck, it was an Equinox front wheel drive with the 2.4. And under powertrain management here, emission control systems will look at air injection. Excuse me. And I just want to look at the description here, and I don't expect everyone to read the whole thing. I mean, you can go to this yourself, whatever you want. But one of the things that disturbed me this week is when I talked about the secondary air system, most students had no idea what I was talking about. So that was a little troublesome because you've all been through, or you should have all been through fuel and emissions before being in this class. So I'm going to review really quickly what the secondary air system does. And its purpose in life is to speed up the catalytic converter getting to operating temperature. When a catalytic converter is cold, it doesn't do anything. It doesn't work. So to get it hot, what they do on some vehicles, not all vehicles have secondary air, they blow air into the exhaust ahead of the catalytic converter, and that makes it heat up faster. Think about if you've ever had a campfire and it's not really burning very well, so somehow you add some air to it, whether fanning it or whatever, and all of a sudden you've got a much hotter fire. So just think of it that way, right? The thing about this, right? It has some temperature parameters, right? So the engine coolant temperature can't be super cold, but relatively cold, 133 degrees. We just talked about how, normal operating temperature is more like 200, right? So this car's been sitting a while. It can't be less than 14 degrees, the intake air temperature. And the vehicle's been sitting for 60 minutes, right? Now, here's the kicker on this. This caused a diagnostic trouble code. It would fail New York State inspection. It would cause a check engine light. And this pump operates maybe for 60 seconds after a startup. That's it. And then if you run into the store or something, come back out, it's not going to run again. It's not going to run again until the vehicle's been sitting 60 minutes and the temperature drops below 133. So, maybe this runs when you go to work in the morning and runs when you leave work at night for maybe up to 60 seconds. So this system, while necessary to speed up the heating up of the catalytic converter, it's kind of crazy that it can cause your vehicle to have a check engine light, fail inspection, and all that for a system that operates maybe up to 60 seconds. So, all right, so end rant. Most of these have some sort of an air pump, and it can be an engine-driven air pump. In the old days, they were. The belt ran around the air pump and spun it. But of course, that's for something that only operates for up to a minute. Now you're driving that pump all the time. That's kind of inefficient. So they switched to electric pumps on a lot of these systems. That way the pump can be kicked on when it's needed and then shut off. So it's only operating while the system is actually in operation, where the belt-driven pump is spinning all the time. This is a way to increase fuel economy by taking it off that belt-driven pump. And not all vehicles even have secondary air. And some just use the natural pulses of the exhaust and one-way check valves to let air flow in but not out. So there's all kinds of different setups. But this particular vehicle, this 2015 Equinox, has an electric pump down near the bottom of the radiator. Those have been problematic because moisture and water and snow and everything can get into them. But that wasn't the case with this one. The pump was fine. And from the pump, so the pump takes air from the air cleaner box, so it's filtered, right? And it blows it into these valves, right? These solenoid shut-off and check valves. And when those valves open, that air is fed into the exhaust. Now, a lot of vehicles, those valves are mounted somewhere near the exhaust manifold, and then some sort of tube or pipes feed directly into the exhaust manifold. On this vehicle, they chose not to do that. So what they chose to do was feed the air into the exhaust ports in the cylinder head. Now let's see if I can bring up a picture, right, of the exhaust manifold here and kind of show you. This is with secondary air, all right? Here's the valve, one of them, right? So a hose from the air pump plugs onto the valve here. There's an electrical connector. Here's the other valve. And then there are these manifold pipes. These are just little pipes. Their only purpose in life is that air injection valve mounts here. Air from the air pump can flow through this pipe and into the cylinder head, right? So it flows into the cylinder head here. There's these little picture. Well, yeah, let me see if I can. So this, I'm going to see if I can circle these, right? So 2 little ports there, and there's 2 more over here somewhere, right? So get rid of that. And then through the cylinder head into the exhaust ports, right? So there's an internal connection from this passage into this exhaust port, and from that passage into that exhaust port. And these passages they're small, pretty tiny. I took pictures of the ones on this vehicle, but here's what we had. We had a code. Whoops, I'm sorry. I have to, I can't get back to my second tab. There we go. We had a code P0411. So here's P codes 0411. And that code is for incorrect airflow detected. And you can read again what the secondary air system's job is and all of that. But the code has the diagnostics for the code. They have you use the scan tool to, let me turn my video back on here. So incorrect airflow, they have you use the scan tool to operate the air pump, right? So it's an electric pump. You can turn it on. So those of you that were Monday morning, you were through this, right? But the rest of you didn't see this part of it. So you use the scan tool to turn the pump on. You hear the pump turn on. You can feel air blowing out of the tubes that come from the pump. Obviously, the pump is not the problem. Good volume of air coming out of it. So the next thing they have you do is operate the solenoids, the air injection control valves. There are 2 of them, and actually watch to see that the solenoids are moving. And you could see that. The other thing we did with the air pump running and operating the solenoids, you could feel the air coming out. You could feel it stopping. So the solenoids were working. They were opening and closing. And built into these control valves are pressure sensors. So the diagnostics had you look at barometric pressure and then compare the sensors, the pressure sensors in the control valves to barometric pressure with everything turned off. So what should they read? If it's a pressure sensor, everything's off, they should read atmospheric or barometric pressure at that point, or be very, very close. And they were. So so far so good on those sensors, pressure sensors working. Then they have you energize the air pump and see if the pressure goes up on those pressure sensors as air flows from the pump through those valves. And first with the valves open, so air is flowing through them, and you get a little bit of a pressure rise, a little bit above barometric. And then have the pump on with the valves closed. So now you're deadheading the pump basically. All the pressure from the pump's going into the valve and it can't get out because the valve is closed. So the pressure goes up quite a bit. When I say quite a bit, it's only a few pounds. The pump doesn't put out a super lot of pressure. But everything was within parameters. The pressures were all exactly what they were supposed to do. So there's obviously no problem with the pump. There's no problem with the valves, they're operating. There's no problem with the pressure sensors, they're operating. So the insufficient flow, the diagnostics kind of dead-ended and said, clear the code, drive it. If the code comes back, well, you still have a problem, but otherwise you're good. It doesn't really take you anywhere else. So what do you do in a case like that? Well, I know what I did, and I'll show you. So go to the vehicle level here, right? And under technical service bulletins, I think I searched for 0411. I don't remember exactly what yeah, here we go. So this technical service bulletin right here. This is exactly the code we had, all right? This came out a little more than a year, a year and a half ago, right? And Chevy Equinox 12 to 17. This is the correct engine. It does have secondary air. So some customers may comment that the mill is illuminated. The technician finds DTC P0411, incorrect airflow set in the ECM. And we did, right? And all the diagnostics checked out. Nothing wrong with the system, but we still have a code. So it says it might be caused by moisture and or ice buildup in cold climate areas. May also be caused by a byproduct of using inferior fuel, creating a restriction in the secondary air injection ports in the cylinder head, causing higher than expected pressure. Right? So what does it do? These pressure valves, or these control valves, when they open, expect a certain flow and a certain pressure. Now, why we got the correct pressure on the diagnostics, I don't know. I'm wondering if there isn't an additional diagnostic for airflow here. If it were me, what I would do is, if I wanted to test the operation, the flow of air into the exhaust, I would watch the oxygen sensor, kick the pump on, and expect to see it go lean as all that air blows in. I have no idea whether that is involved in the diagnostics. I'm just saying I've seen things like that before. So, first thing they have you do, this is the plastic hose that comes from the air pump to the air valve. And what they're showing, I don't know how clear it is here, they're showing ice buildup in there. So if you got condensation, you got moisture in there, and then it freezes, that could cause the lack of flow. This vehicle had the problem in, right now it's in the teens or maybe single digits. It's cold enough that this could have been the problem, so very believable. However, we did not notice any ice buildup or any particularly high level of moisture in these plastic tubes. So the next thing is to check these ports. Now, these are the ports in the cylinder head that I showed you a little while ago, and the tubes that feed the ports. And when we took this tube off, this is, for those of you that were in for the beginning of this diagnosis, and then in the afternoon we got these tubes off, this is exactly what the tube looked like in the little manifold that feeds into this port here, right? Sort of plugged. And these ports, I have pictures. I took them on my phone. I'm going to have to. I'll squeeze them into this video. But I can't do that right now. So it'll be a little gap, and I'll squeeze them in. But I got pictures. Bottom line is, these ports are supposed to feed into the exhaust port here. There's supposed to be a connection between the two. And when we got this all disassembled, it was very visible that these ports were not full size. They were close to plugged at the opening. And then when we tried to put something through a little piece of wire, they were completely blocked. So there was no, we sprayed some cleaner in, and the cleaner just sprayed back at us. It should have instead come out the exhaust port because it's supposed to be connected internally. So, we used brushes, wires, cleaner, and it took an entire morning lab Tuesday morning to get these 4 little ports cleaned out and flowing well. And the manifolds were relatively easy to clean out. So again, let me go back to, just show you where we were working. So on the exhaust manifold, with secondary air. So where these pipes here, right? So the end of this pipe bolts on to where these little ports are here and there. And these 4 ports were absolutely and totally plugged solid. So kind of a pain, we had to drop the exhaust, we had to pull the exhaust manifold off and all that, but got them cleaned out, cleared the code, and the vehicle's back out on the road, and so far, so good. Put everything back together. So similar now, right? Hang on. Similar to that story with the Jetta, where it was blaming the engine coolant temperature sensor. So the diagnostic trouble code points you at a sensor, points you at an electronic issue. It was really a mechanical issue, being the thermostat. And with this Equinox, the complaint is about the secondary air system, and all the diagnostics look at the pump, the solenoids, the pressure sensors, etc. And all of that was working fine. There was no problem with it. The problem was a simple mechanical blockage, just carbon. Now, if I own that vehicle, this vehicle had 50,000 miles on it. The bulletin blames the possibility of poor, bad fuel, right? I don't know where you get inferior fuel. The question came up among some students, well, maybe they should be running higher octane. Instead of running 87, maybe they should be running 93 octane. And I had to explain, and so I just want to make sure everybody realizes the octane rating of fuel has to do with anti-knock. It doesn't have anything to do with how clean that fuel burns. So higher octane fuel, lower octane fuel, it all has to do with the additive packages in the fuel, the detergents, and whether there's any kind of contaminants. So if fuel is coming from, one of these big suppliers, and then the pumps and the tanks and all that are certified by inspection agencies, I don't know how likely it is that you're getting inferior fuel unless you're buying it, somewhere out of the main supply chain. Anyhow, that's what the supposed cause. And the thing that's really troublesome with this particular vehicle is it had 50,000 miles on it. We did this job. What do you think is going to happen in another 50,000 miles? It's going to be all apart again. So really kind of not super thrilled with the design there and how small those passages are and how easily they plugged up. Okay, so that was my little aside into diagnostics that, like I said, usually this waits till the end of the semester. Usually after we've learned how everything is supposed to work, then we talk about what can go wrong and how to diagnose it. But I had the opportunity. It's all fresh in my mind. A lot of you have seen it. Some of you that are watching this spent, several hours involved in trying to clean those passages out. That was not fun. It was kind of a dirty job. And several of you spent time with the disassembly and the reassembly, but it worked out well. All right, I'm going to go back to the slides now. So let's find those slides. And, we had talked about thermistors. Now I just talked a little bit more about thermistors. And the next thing to talk about is potentiometers. So let's scroll down to that, right? Go through all the stuff we already looked at. Okay. So that's the list of inputs. And we talked about thermistors. So if I just recap quickly, they are resistors which change according to their temperature. If the resistance goes down when the temperature goes up, that's called a negative temperature coefficient. And that is most of them that we deal with. If the resistance goes up with the temperature, that's called a positive temperature coefficient. You could see that. We don't usually. They're used to provide temperature information to the computer, so that could be coolant temperature, cylinder head temperature, intake air temperature, ambient temperature, transmission oil temperature, engine oil temperature. Anywhere they want temperature information, they slap a thermistor. They all work the same, they just may be packaged differently. The voltage sensed by the computer is dependent on the temperature of the thermistor, and they have two wires on them. Those two wires, as we talked about, and you did the temperature sensor worksheet, they are the 5-volt reference, which is also the signal wire, and a ground. The ground typically runs directly back to the computer so that the measurement is more accurate. There's a picture of one. So how many wires does it have? It has two. What type of information does it provide? It is a varying analog voltage. So it has all kinds of possible values, not just on and off like digital would be. And it's used, that voltage level is used to determine what the actual temperature of something is. So on to potentiometers. First thing you'll notice about a potentiometer is that it has 3 wires. And we'll talk about what those are. But what are they used for? I talked about this in the lab video. These are used to provide position information. So accelerator pedal position, throttle position, blend door or mode door position on an HVAC system. Had another example that just came up the other day that now escapes me, but anytime the computer is looking for some sort of position information, it's likely to be a potentiometer. The voltage coming off of this varies according to position of what they call a wiper. This is the movable part inside the potentiometer. They have 3 wires, typically a 5-volt reference. And you should be noticing a pattern here, right? That the computer systems, not just in cars, most of them use 5 volts as their reference. I think if you look at a USB port on a computer, you're going to find that's 5 volts. So this is a very industry standard electronic sort of thing, is to use 5 volts. Back in the early 80s, when computers were really kind of new in cars, if I remember right, because I was just getting into it then, the reference voltage on the Fords, the Lincolns that I first looked at was 9 volts, I think. And the trouble with 9 volts is it's too close to the vehicle's battery voltage level. But the 5 volts, you're never going to drop below that when you're cranking the engine or anything like that, right? So you've always got that 5 volts available to the sensors. And that comes out of a voltage regulator built into the computer. And so you know that when your battery voltage is changing all the time, right? If you have a voltmeter on your battery and it's reading 12.5 volts with the engine off, when you start the vehicle, it's probably reading more like 14.5. If you turn on the headlights and the rear defroster and the blower motor on high, and then the engine cooling fan kicks on, you know, that 14.5 volts might drop down more like 13 volts. So it's all over the place as you're going down the road, day, night, hot weather, cold weather. Is the air conditioning on? Are the headlights on? You know, that battery voltage changes a lot. This 5 volts never changes. It's a voltage regulator inside the computer. So we have a nice, steady voltage level supplied to all of our sensors. And the ground going directly back to the computer, same idea. If you ran the ground wire, you know, to the engine block, and then from the engine block to the body sheet metal, and then from the body sheet metal back to the computer, any corrosion in those connections is going to reduce the voltage seen at the computer. So it's going to throw those sensor readings off. By having the ground go right back to the computer, we're measuring It's like putting a voltmeter right on the sensor, right? Think of the reference voltage lead, or I mean, think of that ground lead to the sensor being like the black voltmeter lead going right to the sensor from the device that's measuring the voltage, which in this case is the computer. And then on a potentiometer, the third wire is the actual signal wire. So the 5-volt wire stays 5 volts. The ground wire stays ground. This third wire, this one, that's the one that actually changes as the position of the sensor changes. So as you saw in the paperclip paper pencil lead demonstration, and feel free to go back and look at that again, right? As you saw in that, as we move the wiper, now the wiper was our middle paper clip, right? The one that was attached that we were reading the voltage off of. As we moved that closer to my positive lead, where I had the positive wire hooked onto the piece of paper, we saw the voltage go up. And as we moved it closer to the ground wire, we saw the voltage go down. So here's a picture of a throttle position sensor, all right? All the things I was talking about. Inside the computer here, right? Little voltage regulator. So regardless of what our battery voltage is doing, that's putting out 5 volts. So you can see that 5 volts is being fed to the sensor, in this case, pin A. We're calling that reference voltage. So the 12 volts is being fed in. That's gonna, it says 12, but it could be 13, it could be 14. What comes out here is always gonna be 5. Every time I stick a voltmeter on this reference voltage wire, it's 4.99, 5.01. I mean, they are very, very close to exact. Here, the ground wire coming back. And notice our voltmeter, basically this voltage sensing circuit, is hooked to that exact same ground that the sensor is. So they're both looking at the same ground reference. And of course, the signal wire. This is the one that really counts, right? So this is being measured as the wiper in the sensor changes. This is the one that's going to tell the computer, you know, at what position this wiper is inside the sensor. So if my sensor wiper is over here, right, then, you know, we don't have much resistance between my 5 volts and my signal. So the sensor is going to see almost all of that 5 volts. And I know I told you this before, but I'll tell you again. It is never normal for it to see all 5 of those volts. Probably a wide open throttle would be like 4.5. If the computer sees 5, it sees that as a problem. If, on the other hand, my sensor, the wiper here, is pointing, you know, more here, closer to ground, right, then that 5 volts is going through all of this resistance here, right? And so most of the voltage has dropped by this point. So the signal wire, you got to kind of ignore this arrow and look at this instead, right? That's what should be the arrow. So the signal wire is almost touching ground, right? It's almost on this ground wire right here. And so what do you think it's going to read? It's going to read very close to 0, which is what ground would be. And so again, I told you, and I'll tell you again, if this computer sees 0 there, it knows that's not right either. So it shouldn't see 0. It should see somewhere. Just write it down, help it stick in the brain. So this should be, you know, somewhere between, let's say, 0.5 to 4.5 volts DC, right? So this is an analog voltage. It could be anywhere. It could be 0.5, it could be 1, it could be 1.2, it could be 1.8, 2.7, 3.5. Anywhere in between those two, this voltage sensing circuit could see. And then inside the computer, there's just a table, right? It's, you know, 0.5 volts equals, idle. 1 volt equals, 10% throttle maybe. 1.5 volts maybe equals 15%, and so on until it gets to 4.5 volts equals, wide open throttle. So the computer just has a chart inside, right, saying that certain voltage levels equals certain percentage of throttle opening. And the same would go if this was an accelerator pedal position sensor, if this was a any kind of position sensor. So let me bring up all data. So back to that, if I can find it right. And I'm just going to go to an older vehicle because, well, maybe not. Let's just look at this. I'm going to go to the wiring diagram. Should never do this without knowing what I'm going to find, but let's see. We'll live crazy here. So engine control schematics, and I want to look at engine data sensors. Oh, wait a minute. I think I just saw throttle controls. They see throttle control. All right. So here, try and make this a little bigger if I can. All right. So what do we have? I have the engine control module at the top, right here. And notice a lot of these, it says 5 volt 3, 5 volt 4. These would be the reference voltage wires here and here. Now, why 2 wires? Well, this is the accelerator pedal position sensor. There is no mechanical connection between your foot as the driver and the throttle plate. So the throttle plate is operated by a motor. If that position sensor goes bad and feeds false information into the computer, you could have a vehicle with the computer's trying to open the throttle when the driver doesn't want it to, or the opposite, right? So it's really critical that accelerator pedal position sensor is accurate. So what do? They have redundant sensors here, okay? So APP1, I don't know if they have them labeled, and APP2. So this is one potentiometer. Going back to my slide, 3 wires, right? We have our reference voltage here on pin C. We have our ground, or what GM calls this low reference, but you can see here that it's actually a ground inside the computer, right? This engine control module, this box here is the same one that's at the top of the screen, right? So engine control module, they're just drawing it conveniently so they don't have to have the wires squiggling all over the page here. And the third wire, right? So from each sensor, there's a third wire, right? This is the movable part of it. This is the wiper. So this is the actual signal wire. And it's the voltage on this wire that's going to change, right? This is always going to be 5 volts, 5 volts. This is always going to be a ground wire. But what the computer's watching, right? It's watching this one and it's watching this one and seeing, as you put your foot into the accelerator pedal, the voltage on that wire is changing. The reason there are 2 is the computer can compare them. And if they don't agree with each other, then the computer knows that one of them is wrong. And if if they're wrong, well, it doesn't necessarily know which one's wrong. So what do you think its default action is going to be if it can't trust the reading it's getting from the accelerator pedal position sensor? It's not going to open the throttle. What typically happens if it loses this sensor, right, if it doesn't know where it's at, is it's going to go into a special operating mode, a reduced power mode, where maybe it runs a little bit above idle speed. And that would be enough if it comes in on the tow truck and they dump it out in the parking lot. Maybe you can get in, it'll run a little bit above idle. You put it in drive, you can drive it into the shop, but the accelerator pedal will be useless. It won't do anything. Or maybe if you're the customer, if you're the driver, and this thing goes bad while you're going along the road, maybe you have enough engine RPM to get off to the shoulder of the road, but you can't drive it normally if it loses trust in this sensor. So these are redundant for safety reasons, and if they don't match, then the vehicle will not accelerate. I want to talk just a little bit about what I mean when I say match too, all right? They are not necessarily the same voltage level. In fact, they might be opposites, so that when sensor 1 is going up, sensor 2 is coming down. They're just wired, differently, or put in there differently. As long as the computer understands what the voltage level from each sensor equals as far as accelerator pedal position, and they both agree on the accelerator pedal position, if not the same voltage, then this will be fine. But if one of them is wrong, then it's not going to trust it. If we go over to here, we have an electronic throttle body. And the electronic throttle body has two pieces to it. So the first piece is the actual electric motor that opens and closes the throttle plate. So, this is pretty simple setup. It's a little electric motor. The computer can energize either one of these wires. The other one's a ground, so it can run this motor clockwise. It can run it counterclockwise, and so the throttle plate will open and close. It does have a default spring-loaded position, but we'll talk about that on the output side. The other piece here, built into this throttle body, you might notice, right? Pins 3, 4, and 5 have nothing to do with moving the throttle plate. What is that? Well, you can tell it's the same as this. It's the same as this, right? In fact, here's a couple more. These are potentiometers. These are position sensors. So where this one here is an accelerator pedal position sensor, and so is this. This one here is a throttle position sensor. And that throttle position sensor is basically the other end of the wire from the accelerator pedal, right? So the accelerator pedal position sensor is telling the computer what the driver wants. The computer is then using the throttle body, this electric motor, to move the throttle plate based on driver demand and things like that, and then looking at the throttle position sensor to see where the throttle plate is at and to make sure that it is following the commands of the throttle body. So it's this kind of feedback loop, right? The throttle body moves upon request from the computer, and then the computer can look to see if that actually happened, see if the throttle body did what it's supposed to do. I'm surprised a little bit. These are normally also redundant. In other words, we have two accelerator pedal position sensors, and just to be clear, they're not necessarily two separate pieces, right? They're in the same housing, right? So if you looked at it, what you would see is one sensor with 6 wires coming out of it. but 3 of those wires are for one sensor and the other 3 are for the other sensor. But the throttle body, that usually also has redundancy. So here's what I'm going to do is let me pick another vehicle. Here, we'll change, and I'll just go to a slightly older Chevy. I don't care. We'll do an Impala 3.5, and look at the diagram for that. We'll do the OE diagrams, powertrain management, and see if I can find the throttle position. Here we go, electronic throttle controls. So this is much more typical. Let me zoom in on this a little bit. Here's our accelerator pedal position sensor, right? We have 2 accelerator pedal position sensors. They are redundant. And then over here in the throttle body, right? Same motor as we saw in the Equinox one, but 1, 2 throttle position sensors. So redundant throttle position sensors. That is more typical of what I've seen, right? So if these 2 here don't agree with each other, vehicle will not accelerate. If these 2 here do not agree with each other, vehicle will not accelerate. So this is all just safety stuff, so you don't have this unintended acceleration, vehicle screaming down the road out of control. There is a difference between these 2 that I'll point out, right? The accelerator pedal position sensor, 5 volts separately to each sensor, ground separately to each sensor. Right? This throttle body, right? It has 5 volts, but then it goes to both sensors, right? And the ground wire goes to both sensors. Oops. So they share the reference voltage and the ground, and then they each have their own unique, there's, throttle position 1, throttle position 2 going out. Okay, so that's, I meant this to just talk about potentiometers and then move on to the next type of sensor, but we had the opportunity with that Equinox to talk a little bit about diagnosis and how that can go, so I wanted to throw that in. It puts us a little behind on the input slides, but it puts us ahead when we get into diagnosis, so I don't mind. All right, right now it is 5 minutes to noon on Thursday. I have to get to the school for a 12:30 lab, so by the time you're seeing this, it's either Thursday night or Friday morning. No test yet. When we get to the end of inputs, so on that on that slideshow listing the different inputs, when we get to the end of inputs, we'll have a test on that. I'll tell you about it. It won't be a surprise. And fair game though. One question I might ask you is what time my clock always says, no matter when I'm doing these. Pay attention to that, right? And if it ever moves, I could throw that on a test just to see if you're awake. Anyhow, I'll see you in lab. Let's see, Monday is President's Day. That's a holiday. So those of you with Monday labs, I will not see you this coming week. Tuesday, I'm taking a personal day, so I won't see you guys next week. But I will be back for the Thursday night class, and I'll talk to you then. Those of you in the Thursday night class, I've probably talked to you, 5 hours after I finish filming this. Okay, that's about it. I'll see you.